Right. We're going to have a few lectures now, about 10 lectures, and I've got my lecture slides on the FLE Minerva labelled 1 to 10. Here, take this. The lectures might overlap, so they're not exactly going to be what first lecture is lecture 1, third lecture is lecture 3, there might be a bit of overlap, but there'll be about 10 lectures. Okay? Lectures are scheduled on, 3 a week normally. I'm putting it down. Monday, I've forgotten now, Wednesday and Thursday, is that right? So this Thursday, I've got a meeting somewhere else. We've cancelled that lecture. That should have gone from your timetable. Can you confirm that? Thursday, it's not there. Anyway, should be not there. That still leaves us with 10 lectures over the next few weeks. It's a bit of a... there's a couple of weeks with me, another week with looking at material science, more material science, timber. Yeah, take those. You got one? And then come back to me, and I'll give you a problem sheet to do. So before you go away for Christmas, you'll have a water engineering problem sheet to do and submit. Okay? So bear that in mind. This handout is the one, as I said, the one handout I'm going to give you on this course. Previously, I gave some slightly different handouts and I've staggered them out throughout the session. But I've changed the style this year and I've given you one with a lot more detail in it. The lectures are going to follow closely the order of those notes. You might want to be doing some extra we'll do some extra example calculations during the time, and you'll need a bit of paper, calculator to do those on. And you might want to make a few extra notes, but these are quite detailed notes. Okay, they're all on Minerva. I was going to show where that is. You know where Minerva is, don't you? I opened this in Chrome and now it's not there, is it? Where's Chrome? I'll forget that. We'll go back to the slides. On the column on the menu in Minerva, there's a water engineering section on the left. Go in there, all the slides are on there, the lecture slides are there, the notes are on there, there'll be examples on there. I've done some screencast videos where he runs through the examples, and those will become visible as the course progresses. So there should be plenty of material. You can always email me and make arrangements to go and see me, or I'll get back to you with a quick answer. Okay? Lecture today, we're going to go through an introduction about water engineering and how important it is. Everyone likes to say how their subject is most important, but nearly everything to do with engineering involves some sort of fluid mechanics. So some people will talk about fluid mechanics. Some courses on the engineering course will be on fluid mechanics. We call it water engineering because most things that civil engineers do in terms of fluids are to do with water, with one exception. What's the other exception? So the other fluid, a gas, air. So we want to get enough air into the room so we can all breathe and be comfortable, warm, not too cold, not too warm, not too hot. Or the ventilation. So ventilation is one of the things civil engineers get involved in, and fluid mechanics that we do on this course is related to the ventilation as well. You don't do much ventilation in first year, you do a bit more in second and third year. When it comes to the building services, you'll do labs on that. So all this course is going to be involved in fluids in all senses, and all the equations we'll see will be valid, or the fundamental equations will be valid for liquids and gases, and we'll come on to that again. So, liquids and gases, that's what I said. Okay. Other gases, wind engineering is another area of civil engineering. It's not water. Again, it's air. So, you know, when you're designing a building, you've got to look at the forces, the wind forces, either on the side of the building or the roof of a building. To particularly the problems with roofs are the suction pressures, the negative pressures which make the roofs lift off. Okay, so we'll come to a little bit of that, relating to that in this course. We're not specifically the forces involved, but why those forces exist. So first few slides here are not in these notes. I'll tell you when we get started onto these notes, will be a bit later. We're just going to talk about the importance. So nearly everything in civil engineering involves some sort of fluid mechanics. What's fluid mechanics? It's just exactly the same Newtonian mechanics that you've seen already in your, you know, from pre-GCSE to A levels to everything that you're going to do now. We're just building on that foundation and just putting it in a slightly different framework. We've got a fluid, you know, you're used to solid mechanics where you've got a lump of stuff with a mass. Now this is, we've got fluids that are moving. So we try and define a mass, but we've got fluid moving through that. Well, we define a volume, and within that volume there's a mass at any point, and we work with that mass, the mass that's in that volume. So we'll get onto it. It's just a slightly different approach, and it's not massively difficult. The approach I take to teaching the fluid mechanics is very practical in that we're trying to solve problems. You can see fluid mechanics courses which are really, really, really mathematical. We don't take that approach. I'll point you to some books. I usually bring a pile of books to show you what are useful ones. And those are very practical books, and I'll point out some that are very, very useful, a bit too heavy. So I'll bring some of those tomorrow. So introduction to civil engineering fluid mechanics with we're going to demonstrate the fundamental ideas and principles, Newtonian mechanics, conservation of energy, conservation of mass. Okay, nothing you've not seen before. And then we'll put these together in some solutions to some straightforward hydraulic components. What do you mean hydraulic components? Water flowing through or over something. Yeah, so sometimes this course is called, in other places, called hydraulics. So water, the mechanics of water. Sometimes fluid mechanics, sometimes water engineering. We've decided to stick to water engineering through all our 3 years. And nearly all of you do water engineering for 3 years. And I teach it all 3 years, so you're lucky to get me. Or maybe not. That's supposed to be a joke, you know. If you're doing architecture, you don't do it in the 3rd year. You're lucky. Water. We're mostly concerned with water, but in terms we're looking at liquids and gases. Okay. Some facts about water I found. Sorry, these are from Electric Cardiff University. Came here to do some we had a big meeting on water, and he gave a few slides, and I borrowed these off him with his permission. So water, let's look at this, the volume of water in the world. So that's the Earth sphere. That big blob of sphere of water is the total volume of water, 1.4 billion cubic meters, kilometers. Okay, so a lot of water. Only 35 million fresh water, that's that smaller, 35 million cubic kilometres of fresh water, stuff that we want to get access to manage, to use for human consumption mainly, or growing plants. But only that tiny little drop sphere there, only that 105,000 kilometres cubed is accessible. So 0.01% of the total volume. Now that's just putting something in some context. We'll never use these facts again, but I thought it was quite a useful thing to look at. Where do we use water? And why I'm telling you this, because it's you that manage, you as civil engineers, or when you go into work, you'll be the person that gets that water to the place where it needs to be used, or takes it from where it is to where it's going to. So water is needed to sustain human life, yeah, you know that, through consumption and sanitation. Now sanitation is a big thing. We need to take dirty water away from people. So if not, people all start dying very rapidly. And it's the sanitation that has managed societies to grow over the years. Support food production. Obviously, you know you need water to grow food. Support energy production. Most of the energy we use requires water. So the electricity power station, it runs on, the turbines all turn because you've got steam and water being heated to turn the turbine, and you need to take that water off and cool it down and manage it. So you've got to manage how much water goes back, how hot water or cold water goes back into the ecosystem. Okay, everything. Sustain industry. So much industry uses water. One of the big things over the past 20 years in engineering, and will be for the near future, long-term future, and be nothing new to you, is about sustainability. I've not written sustainability on there, but maintaining ecosystems, biodiversity, and ensuring that everything can be sustainable over the very much longer term. And that's what we have to think about in all our designs of anything we do now. Not just about carbon counting, how much energy concrete uses or steel uses. It's also about how we manage the resources in the designs that we're using. So if you're managing something that moves water around, how can you do that in the most efficient way for both the use of the energy and the use of the precious resource that water is? So accessibility of fresh water. 70% of fresh water is locked in ice. Aquifers. Aquifers are the underground stores of water, natural stores of water. They're being drained very quickly. With climate change, you've got different levels of water. In the sea, so you talk about sea level rise. Sea level rises, more salt water goes into the aquifer becomes not full of potable water, drinkable water. So we need to think about managing that. Now we don't look much at aquifers and underground water until you start thinking about wells, and we'll see a little bit of wells in probably a second and third year courses. Two-thirds of the water, and we think about water about drinking most of the time and washing, but two-thirds of the world's water is used to grow food. So you, as an engineer, and you're trying to move water to somewhere, it's about getting it to a place where it's used, and two-thirds of that work will be to getting it to the agriculture. so not a water fact here, but population growth. 83 million people live on the planet each year. We need to work on planning how much water we will need. And again, that's about what civil engineers need to get involved in. We won't be doing this on our course here this year, but you'll start thinking about water resources. That's another subject area that gets taught in civil engineering. How much planning for the use of water in the near, short future and long-term future. And there's a lot of people that say that the current demand for fresh water is not sustainable. Well, that will be part of your job when you get working. Good thing for civil engineers. Take that. So what I'm saying, that water is really important. Civil engineers are the people that get that water to where it needs to be. So there is always going to be lots of work in the water sector for people like you who know how to do this this engineering problem. And the other thing is this last point. Politicians don't really want to spend any money unless they seem to be getting some advantage. And this last point is not just political, it's economic growth thing. Every $1 or £1 invested in water provides an economic return of 8 times what you put in. Okay, there is a lot of money being invested into water, and there will be forever as long as the population is growing, and that's not looking like stopping for another 30 years or more. Some facts now, more facts about water security. So we often see things about water security coming up. This has been a big political issues. Some challenges. 1.2 billion people have no access to safe drinking water, and 2 million people die annually of diarrhea. Huge numbers. Situations that none of us have been in. We've always got access to drinking water, and all the sewage is taken away. All the dirty water is taken away. Really a challenge in the world, and that's being worked on. There's the Millennium Goals, the Sustainability Goals that are addressing these 2 points. So 1.2 billion don't have enough access to water. 2.4 billion don't have access to basic water sanitation, toilet, and separated from the sewage. Big challenge. And this gives not only diarrhea, but maybe hepatitis A. It's also a problem in terms of gender. When people don't have water, it's usually the women that have to go and get that water, bring it back to the family. So, another political issue. Flooding, much more accessible for us. We can understand what flooding is. So flooding often causes many deaths worldwide. So a bit old data this, 2004 tsunami in Indonesia killed 250,000 people. Flooding in the UK, is that a big problem? We hear about flooding, not many people die in the floods in the UK. Still, one's too many. But we need to think about it. You will be working in flood management in the UK, and usually protecting property and the economic impact. But flooding is also a challenge that causes death. Natural disasters. And also, another fact makes water more costly, importance of not having water more costly. More than half the hospital beds in the world are filled with people with water-related diseases. The key to solving all this is getting clean water, more clean water, enough clean water to people. In fact, enough water, even if it's a bit dirty. More water is better than no water. You might not believe that, but that has been shown to be the case. Get more water to people. Okay. You've seen that fact. There's just a picture of a drain. So I said 2/3 of the water goes on food. Well, there's 70% on that figure. But water stress. Are we short of water in this country? It's chucking it down today, over the weekend. Yet, if we look on this picture here, southeast of England is classified as having been water stressed over this period, and we'll see all these red regions here. You might say, well, Africa, yeah, it's hot there. There's a lot of water. You know, it's North America, California. They've got wildfires going on. That's not California, but around here there's wildfires every year because of climate change and population change and water demands. This figure is showing how things will change. Oops. So it's looking, everyone looks at where they come from. So look a bit closer. It's actually got slightly worse there, but nowhere near as the amount of red that's occurred in Africa and the middle equatorial countries. Sorry, what am I saying here? Population increased by over 50% next 50 years. Urbanisation actually is causing huge problems because getting water into urban areas, you might think because it's a bit of a smaller area, you can get more water there. But urbanisation causes more disease problems. Taking the dirty water away is very problematic. If these urban regions are on the coast, we've got sea level rise, climate changes, so bigger, shorter storms maybe. You've got problems to deal with. And again, civil engineers, we're dealing with these problems. We need to increase food production. This is all doom and gloom, isn't it? But planning for sustainability is the thing that is important. And you're the future that will be doing that planning and working in this industry. And one of the things to do some planning is working out, well, how much water is used for everything. And you know of carbon counting. People talk about counting carbon. Well, another way of counting energy use or resource use is to put things in terms of water. Okay, so we talk about water footprints instead of a carbon footprint. And then we also talk about the local water footprint and the virtual water footprint. That's using water in another country, which a country might not have that water, yet they need the economic. They need to sell things to make economic balance their economies. So anything that we might buy will cause water shortages in other countries. We need to think about that. One of the things that's become very popular recently about the amount of water required to grow meat instead of vegetables. A kilogram of beef, 15,000 litres of water. Sounds a lot. Kilogram of wheat, 10 times less. So the idea, part of the rise in veganism is about this argument, the energy used, but it's not just energy, it's water. So let's just have a quick look at some water footprints. Embedded water in a cup of coffee, 140 litres. So we're talking about embedded water. This is about how much water it takes to make a half-litre cup of coffee. A bathtub full, 140 litres. Some beef, quite a lot of water there, 3,800 litres. 26 bathtubs. Pair of jeans, this was surprising to me, 10,000 litres. All the cotton irrigation of the plant to make a pair of jeans. And we buy and throw these away, don't we? After using them, of course. Is water too cheap? How much does water cost? Anyone know how much you pay for water at home? Because none of you pay for water at home, do you? About £1 a cubic metre. Maybe any advances? How much does that bottle of water cost you? You might have paid 50p for that. Huh? 20p, that's a cheap bottle of water. Well, it sounds cheap. However, so I've got these numbers, sorry, they're in dollars, but it's about £3.50 I looked at my water bill, I paid about £3.50 for a metre cubed. 1,000 litres, you got a metre cube, this big, right? Is that a lot of money? If we wanted to get people to reduce their water consumption, would we double the price of water? Would that be a good thing? That's usual way of getting people to stop using things is to raise the price. We've done that with sugar. We don't eat as much sugar anymore because they've raised the price. Very unlikely to happen with water because water is an essential resource. So it's not quite as easy to do things to change the price of water. In countries where they're very short of water and people can't afford water, they don't cut water off because it's one of the essential. Some places do cut the water off. Okay? It says on there, how much water do we use a day? Have you ever thought how much water you would use a day? Well, it says on there, about 150 litres a day we use on average. Yeah? So about 600 of those little bottles a day. That's for toilets, washing, cooking, eating, drinking. Okay? So that's part of the water resource calculation the city has to do to get to build the reservoirs, to plan ahead. Some other pictures. So you might pay about the same for a pint of beer than you would for a litre of 1,000 litres of water. But then again, you might pay similar price for the small bottle of water. Okay. So, in civil engineering, why are we studying fluid mechanics? Well, you've seen all those things how important water is, and civil engineers get involved in doing that provision and that management of the water. They get involved in the provision of essential supply of potable water, drainage and sewerage, and ensuring health. So you probably all have heard the idea that engineers have saved many more lives than doctors, and it's because of supplying water and taking dirty water away. Okay? It's not a false fact, it's fake facts these days. It's a truism that you need, the more water you've got, the more health you've got. the less death you have. Most civil engineering projects involve water, sea and river, water distribution, hydraulic design of sewage, dams, reservoir, irrigation, pumps and turbines, water retaining structures. What's a water retaining structure? It's a tank. Water tanks are scattered around the city so that that's pumped locally. Do you know where the nearest water tank is here? Out in the street. You know, the library pub down the back, between that and the park. There's a big water retaining structure there. So it's a Yorkshire Water own that, and that's a local tank to pump water into into this region. There's a spillway on a dam. We're going to look at doing some analysis for flow over a dam wall like this, over a spillway. You'll do a lab in this course, which involves looking at the relationship between how much flow goes over and how deep the water is. Okay, that's a key thing to understand. In fact, what we want to do, and the fundamental thing we want to do, and we're looking at flowing water, is how much water is flowing and how big a thing we need to make to allow a certain amount of water flow, or air flow, or whatever gas flow at the rate we want it to flow, and not be too deep or too fast. Okay, it's controlling the water flow like that. And this is for the rivers, the reservoirs full. We need to say, well, how much water goes into it? Do we how big does this weir need to be, so that once the reservoir's full and the water's still flowing in, how big does this overflow need to be to allow enough water out without the reservoir getting too full? Okay. So it's designs of structures like this. This is more straightforward and interesting than possibly the social issues of hydraulics, but it's the social issues are important for your future potential. Might get involved in looking at big things like these dams. The Hoover Dam. So what we will be able to do calculations from these lectures on the forces on this dam wall. It's a very, very high dam, 221 metres high. The pressure at the bottom of that dam is extremely high, huge amount of concrete. So we can work out the forces on this and say how much concrete, how much force do you need to resist to keep this dam wall up. Okay, it's quite an easy calculation, and we'll see how to do that. Well, hydroelectric systems. We don't get really involved so much in these, but we will see some examples, some problems where you can work out what the pressure and the flow rate is at the end of this tube. A tube that goes down to a turbine is called a penstock for some reason. But we'll be able to look at structures like this and look at the forces and the pressures involved and the flow rates in tubes like this. Okay, that's part of the course we'll do. More mundanely, great big dam structures, we'll look at flows in channels like this. We don't do much channel flow in the first year, but we will look at you do in third year, and designing the size of drains like this is part of the civil engineering hydraulics that you have to get involved in. Not so exciting, but important. Hydroelectric power stations, bigger pipes, drainage systems. So this is probably, I'm not quite sure what this is, but it's either a drainage system or water supply system. It's probably a drainage system, but these are very big pipes. So this is a picture of all the water pipes. I'm going to turn this down. I did a research project with Yorkshire Water, and we were looking at all the pipes in Yorkshire and looking at the connectivity. So here we are in Leeds. Now you can't really see the pipes. Zoomed in a bit, you can see a few more pipes. You can see, where are we in Leeds? We're about up here, just next to the park. That's us. We'll zoom in once more. Can't really see the detail, but this is all the water delivery pipes, not the ones that come into your house, but they go in the street near you. Hundreds of thousands, if not millions of pipes need to be analysed. And you'll look at pipe flow in second year in more detail. We'll look a bit of it this year. Another thing you might look at. We're not going to look at wave forces from waves, not waves specifically, but we will look at forces of jets hitting targets, hitting curved walls like this curved wall. You'll do another lab where you look at these forces. That's the Newtonian mechanics. Rate of change of momentum is equal to the force. That's what we'll see in the lab. We have to look at drains and sewers, design the size of the sewer. Ports, more drains. Sewage works, really important. Environmental flows. So while we're not going to be looking specifically at environmental flows in this course that we're doing, we're going to be looking, you will have the opportunity in third and fourth year to do projects involving environmental flows and pollution within the flow. Enough examples. Where are we now? Got 10 minutes. We'll get into doing some more, some things from the notes. So I've mentioned water, flow of air around buildings. We're looking at a building, you might get forces like this. Well, these are suction forces, these are pressure forces, suction. Or the roof, you've got suction forces. Okay? So you want to know this building in Leeds? Tallest building in Leeds. It doesn't look the tallest because it's low down. There's lots of things that are higher. Bridgewater Place. This has problems with the flow around the building. They've actually built now some fancy shaped, what look like fancy bus shelter things, but they're not bus shelters, to change the airflow at ground level because this building was causing a lot of turbulence, and spiralling flow, and it ended up being extremely dangerous. You got 80 mile an hour winds, and at some point some lorry got turned over there, and actually someone did die, which is why they've changed the well, they closed that place off, that road off during high winds, and they've also changed the structure of the or they put some structures in there to change the airflow around the building. So that's one. This is fluid mechanics. It's not the normal stuff we're looking at in the first and second year, but what we do in this course does relate to the reasons why these phenomena occur. You might look at airflow over buildings in a wind tunnel like this, or do some computer modelling. So this thing, looking at airflow around buildings or looking at airflow around buildings in a computer, is something you might do in the third and fourth year project. More buildings, or stadium. I'm going to skip over these, too much. Right, just quickly, I'll finish off with a few things about the course. You've got a 3-hour exam at the end, not until May, 80%. You've got 4 labs. You do one with materials, that's in the next few weeks, 5%. You've got 2 with water and 1 with soils, and those are done in the weeks when the other half of you are going surveying. Okay, so that was being you don't have lectures that week, but you have some labs that week. Okay? That's in March. And those two actually don't have any marks, but you need to go to those, and actually they will be essential for learning what you need to learn for the exam. We do have 2 problem sheets, one in water and one in soil. You get the water one before Christmas from me. And we have next February, you'll have a multi-choice question in here. We sat here doing a half-hour question paper on combination of water and soils. Okay, so that's all the assessment for this module. Well, that adds up to 100%. So you get lots of preparation. It's quite a complicated module in that we've got seemingly about 3 different subjects, but we try and tie these all together and cover all the material. It's not a joke. Resit. There's always a resit opportunity, 100% exam. Don't get into that situation. You're much better off not. One thing, it says on the bottom here, homework, self-study. Apart from the problem sheet, I have got at the back of these notes, quite a lot, so from page 117 onwards, quite a lot of examples for you to do. That's not for you to start right now and get working on those. They're more of revision type things, or when you get the problem sheet, go and look at similar ones and find the solution. Solutions are available online somewhere, or they will be. Okay, so there's an awful lot of support material for this module. Right, books. Now, because I didn't bring the book with me, the pile of books with me, I'll bring them tomorrow and just show you those. And then we can start properly on the course. Okay, we'll finish there now.